Welcome friends to my YouTube channel Sommo Physics. Now on my previous few videos I shall discuss first law of thermodynamics. That is my in first videos I start thermodynamics and I completed the first chapter of thermodynamics, and then I make two videos on classical mechanics, two chapters. One is central force planetary motion and other is gravitation. Now today I shall discuss about second chapter of thermodynamics, which is heat engine and refrigerator. Okay, that is heat engine. Okay, now we all have heard about this term. What is heat engine? Okay, now we know that any mechanism that can convert the heat energy into work is called a heat engine. Okay, and any mechanism for the conversion of heat energy into mechanical work is called heat engine. Okay, now here there are many type of heat engines, but here we are mainly discuss about Carnot engine. Okay, Carnot engine. Now Carnot, there was a scientist Carnot who invented an ideal engine which is free from all defects and imperfections, and in which all the operations are performed in a reversible manner. Okay, all the operations are performed in a reversible manner, and this engine is free from all imperfections and defects. Okay, he gave it a name Carnot engine. So Carnot invented the Carnot engine, which is free from all imperfections and defects. Okay, Carnot invented an engine which is free from all defects and in which all the operations are performed in reversible manner. Okay, this ideal engine is called Carnot engine. Okay, this ideal engine is called Carnot engine. So this is the definition. This ideal engine is called Carnot engine. Okay, so this type of engine was invented by Carnot, and this engine is free from all imperfections and defects, and in which all the operations are performed in a reversible manner. Okay, so what is reversible and irreversible process, that we discuss about in later. Okay, now so a question will arise that what are the features of this Carnot engine? Okay, so there is a basic question that can arise to all of you, that what are the features of this Carnot engine. So there are some basic properties of Carnot engine. Okay, so that I am going to tell. Okay, so what are the basic properties of Carnot engine? So number one point is that this engine always works between two temperatures. At high temperature it absorbs heat from source, and there at low temperature it always rejects heat to sink. Okay, this is at high temperature, and this is at low temperature. Remember there are three parts of a Carnot engine: a body at high temperature source, a body at low temperature sink, and third one is that the working substance. Generally we take a perfect gas as working substance, so there are normally three parts. One is source, which is at high temperature, the second one is that sink, which is generally at low temperature. Okay, and the third one is that the working substance, which we can use here a ideal gas or perfect gas. So there are three portions of Carnot engine. Okay, so what are the basic features? So first feature from which we can say that this engine works between two temperatures. At high temperature it absorbs heat from source, and at low temperature it rejects heat to sink. So this is the first property. Okay, so high temperature it absorbs heat from source, and at low temperature it absorbs heat to sink. Now the second property is that the efficiency only depends upon source and sink temperature. Okay, so it is generally independent of the nature of the working substance. So no matter what working substance you can use it, no matter, because the efficiency only depends upon source and sink temperature. Okay, so its efficiency is eta. Eta depends upon source and sink temperature. ঠিক আছে, sorry, এটা depends upon source and sink temperature. And it is independent of the working substance, or you can say the nature of the working substance. Okay, so no matter what working substance you are going to use, because efficiency solely depends upon source and sink temperature. Okay, so these are the two main properties of Carnot engine. Okay, so another property that I am going to tell you, what is that? The third property is that we know that this is the concept of Carnot engine is purely a theoretical concept. Okay, the concept of Carnot engine is purely a theoretical, because we cannot construct a perfect engine. Okay, so its concept is purely theoretical, since we don't construct any perfect engine. So since there is no perfect engine engine always be practical, so efficiency will be always less than 1 or 100%. Okay, so efficiency will be always less than 1 or 100%. Okay, but the concept of ideal engine is purely theoretical, remember it. So I can write it: the concept of ideal engine is purely theoretical. Okay, purely theoretical. Okay, so must remember it. Okay, now the next question that arises: what is Carnot cycle? Okay, what is Carnot cycle and what are the steps? What is Carnot cycle and what are the steps? Okay, now Carnot cycle is what? The It is a cycle where the working substance starting from a particular point and returns to the same point. Okay, so here the working substance starting from a particular point returns to the initial state. Okay, through two successive expansions and compressions. Okay, I have told about the indicator diagram in my first videos, and remember that when I made my first videos, so there was no board. I did it in papers. So if you have any questions regarding first law, then you can easily ask me. Okay, so if I draw a indicator diagram or pressure volume diagram, then by two successive expansions and compressions, the working substance returns to the initial state. Say this is the initial point. Okay, so the cycle looks like this. Okay, so there are four steps A B through which we can there is isothermal expansion. Okay, isothermal expansion, and the BC, this is adiabatic expansion. So you can clearly say that there are two successive expansions, okay, along AB and BC. In CD we have made the gas is compressed isothermally, that is isothermal compressions. Isothermal compression, and along DA there is a adiabatic compression. Okay, there is a adiabatic compression. Okay, so these are the four steps through which the working substance is brought to the initial condition. So this complete cycle is known as Carnot cycle. Okay, this is known as Carnot cycle, where the working substance is brought to the initial state. Okay, so this is that. Now in our next video I will discuss about the operation of a Carnot cycle, that is how much amount of work has been performed during the entire cycle, and later by using this we can find out the efficiency of a Carnot engine. So that we will do in our next class. Now one of my friends told me to explain one thing that we have taught in first law of thermodynamics, that why adiabatic curves are more steeper than isothermal curves, that we don't understand. Okay, so let's understand that. His question is that why adiabatic curves are more steeper than isothermal curves. Okay, so let's do that. Now we all know that in adiabatic process Boyle's law holds good. That means you can say PV this is equals to K. So if you differentiate it, what we get? P into dv plus v into dp, this equals to 0. Now if you draw indicator diagram, if this is p and if this is v, so what will be the slope? Dy dx, that is dp dv. So for isothermal process, this is the slope that we can write minus p by v. So give it a name 1. And what relation holds good for adiabatic process? P into v to the power gamma equal to constant, where gamma is nothing but the ratio of two molar specific heats. Molar specific heat at constant pressure and molar specific heat at constant volume. So if you do differentiation, then you get v to the power gamma dp, p into this is gamma v to the power gamma minus 1 dv equal to 0. Now from which you can find out that dp dv adiabatic, that is the slope of adiabatic curve, which we will find minus gamma p by v. So by using 1, we can write this is gamma multiplied by dp dv isothermal. So up to this it is fine, okay. Now you all know that for gases gamma is always greater than 1, that you all know. For gases gamma is always greater than 1. Why? That we will learn in heat that for monatomic gas gamma will be 1.6, for diatomic or air it will be 1.4, for triatomic it will be 1.3. So in all cases for gases gamma is greater than 1. So if gamma is greater than 1, this term is larger than this term, okay. So that's why adiabatic curves are more steeper than isothermal curves, okay, because the slope of adiabatic curve is always larger. And if we draw it, then this is the adiabatic and this is the isothermal, okay. This is the isothermal and this is adiabatic, okay. So this is the result, okay. So dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest updated videos, okay. Thank you.